Prof. So today I'll be talking about the math modeling section for our design thinking and innovation project. So basically, we have identified an open space outside of the signature that is large and spacious. However, in our observations, we realized that the area is actually underutilized and lacks a lot of human traffic, in spite of all the amount of office workers that go to work to the signature on a daily basis. This open area barely receives any attention. So our plan is to redesign the place to improve the interaction with the office workers as well as with the environment around it, yet while still maintaining privacy. So in our design, we have split the open space outside the signature into multiple small sections utilizing the water feature that surrounds it. So specifically for this project, we have decided to use our interactive water feature, which is the water spouts, to assist in masking the conversations that people might have with one another. So it's really through the noise generated by the falling of water that we use to mask the conversations and increase the privacy that people can have while they have their conversations. So our prompt statement is, how would the projectile motion of the water stream affect the quality of sound generated after being shot out from the outlets? So while we do recognize that our prompt statement might seem very vague and broad, so therefore we like to specify the terms that we've used. So in terms of sound generated, the sound is produced by the water stream when it falls and collides onto a surface. Next, when we mention the term of projectile motion, so the projectile motion of the stream refers to the height, direction, and shape of the entire water stream. And all these are variables which we have determined to be affected by the flow rate of the water pump, the angle of the outlet, and the height of the outlet. So these three will be the ones that we will control during the experiment later. So next, we also recognize that quality of sound can have many aspects, and such we have split it into two different criteria of sound level and sound texture. Sound level is what we would refer to as how loud and how soft the sound is, which is measured in decibels, whereas sound texture refers to the type of sound generated, and we will touch more about this later in the experiment. And lastly, so for the final decision, we have utilized a variable called the optimal sound quality, which takes into consideration the two sound level and sound texture variables. And what it does is that we will arrive at a sound quality that will be just nice for people to have conversations and not too loud or too soft such that it barely achieves its purpose. So in the whole simplification of this experiment, we have a couple of assumptions. Firstly, the outlets in the piping are all constant in their shape, size, and separation. And this is really to ensure that any changes to our results is solely due to the variables that we are in control of and not other external factors. Next, we assume that there is a direct correlation between the water pressure and its flow rate, and for simplicity's sake, we will only be changing the flow rate of the pump and seeing its effect on the quality of sound. Lastly, we understand that sound can vary when you hear it at different distances, and as such, the sound level will be measured from a fixed distance of 5 cm away. And while each seating area in the different sections might not be of an equal distance between that of the impact and the whole seat, we assume that the variation in distance is negligible, and whatever data that we get in our experiment will be what we use to calculate the optimal sound level. So, onto the formula. Firstly, we have sound level SL, which is proportional to height H, flow rate WF, and affected by the angle theta. So given the level of proportionality, units are not considered. Therefore, sound level is given by height multiplied by flow rate multiplied by sine theta, for a value of theta being from 0 to 90. And next, we have optimal sound quality, which is given by sound level minus the ambient sound level multiplied by the sound texture. And in this case, the difference between the sound level and ambient sound level cannot be a value that is greater than 15. So later we'll touch more about this, but the idea is that for values greater than 15, the volume would therefore be too loud and actually disturb the conversation rather than help in masking the conversation. So onto the variables. Firstly, as seen above, we have the water flow rate, which is given by WF. This value is given by the setting on the water pump, and it measures the amount of water pumped through the pump per unit time. So in the case of our experiment, we have only two options of high flow rate and low flow rate. Next, we have the height of outlet H, which is given in centimeters. So this value is given by measuring the distance from the center of the outlet to that of the water level. Next, we have the angle of outlet theta, which is given in degrees, and this value is given by measuring the angle between the outlet and the water level, with the water level being taken to be against the x-axis. Next, sound level, as we mentioned above. This sound level is recorded from the impact of the falling water or at a distance of 5 cm away. This value is measured in decibels and is obtained by the formula as shown above. Next, we have sound texture. So the different sound textures that we recorded in the experiments were actually given a value only after when we surveyed 50 different people and we had them to rate the favorability of each texture. Next, 6, we have the ambient sound level. So this value is given by measuring the ambient sound level at the location. And this value is also measured in decibels. And lastly, we have optimal sound quality, and this value is what determines the final decision in which the projectile motion is deemed most optimal. So through our research online and experimentally, we have found out that the average human conversation has a sound level of 60 decibels, and the optimum level to mask this will actually be 15 decibels higher. Therefore, previously we had the limitation where sound level minus the ambient sound level should not be a value greater than 15. And so this is all done and calculated given the current distance of the impact from the seating area that we have in mind. And when taken into consideration together with sound quality, we can then make the final decision. So actually, in cases where the difference in sound level for two different scenarios are both equal to 15, then in that case, the scenario with the highest sound texture would therefore be preferred. So for our research, we've conducted an experiment in an enclosed room without any external noise disturbance to ensure really accurate and reliable data. And in this case, the ambient sound level was taken to be at 60 decibels, and the outputs we calculated were at the height of water from water level, the sound level, as well as the horizontal between the launch and its impact. So actually, specifically for the last part, we did it so such that the piping and the water that shot out from the piping does not actually exceed the width of the waterway, and is at a point where any water that shot up will actually go back into the waterway and not affect the passerbys who are using the platform. So firstly, as you can see, we have a table of experimental data that is given at a high flow rate. And after which, we have plotted all the values that we have onto a graph. Next, we have one done at the low flow rate. Similarly, the values will also plot on the graph. And this is the table of experimental data of distances at different flow rates in terms of both the vertical and the horizontal distance. Lastly, in the table 1.4, we have the survey data where we give people the various sounds and the location of impact, and we got them to rate which was the most favorable sound to hear while having a conversation. So, all in all, through our analysis, we realized that to achieve the ideal masking effect, the ideal decibel level that a water outlet must produce should be at 75 decibels, and that given that a normal conversation hearing threshold is about 60 decibels. So for our model, actually, I think one of the strengths is that it's rather simplistic, but yet also very comprehensive and can be tailored to different scenarios with different ambient sound levels and to take into consideration different factors. Next, it is also very easy to change the type of water outlet used and really conduct another experiment, as we do not have any limitation or any preference on that part. In terms of weaknesses, however, the model, as said earlier, does not consider for variation in the distance of the seating area to the impact of the water falling, as what we have done is assume that the distance is negligible. However, to be more specific and actually more detailed, the results would have a difference as compared when you use this model and we do it and take into account each individual distance. Next, we have another weakness, which is that the model assumes a linear relationship between the variables, and this might not necessarily be realistic since there may be external factors in play such as the density of water. Lastly, using experimental data might not be accurate since there may be human error when taking our measurements. So even though we had run the experiments a couple of times, 2 to 3, and taken the average, it may still be really prone to human error, and we may have actually skewed our results. So in conclusion, to achieve a masking effect of 75 decibels, we realized that for our project, the water outlet must be angled at 90 degrees, have a height of 2 centimeters, and using the pump at the maximum flow rate, such that conversations can be masked and privacy can be achieved. And all in all, while we feel that maybe the model might be overly simplistic, and definitely it might not be able to give the best representation of data, however, we feel that if the idea is to really just get a rough gauge of the optimal sound quality, we feel that our model actually more than does enough and really gives you that vague idea. And if you want to really go into detail, then perhaps the formula could be further tuned and the data could be really made more detailed. And this concludes the presentation for the mass modeling.